So today's class is going to be a revisit of design of counters. Okay, and this is going to be in your module 5. This is a very important concept, as I mentioned many times. Okay, because any counters for that matter, should be designed, and you should understand the specifications. So when I say understand the specifications, it means you should understand the design, what is asked. Okay, whatever is asked, that one you should be able to understand. So if you have understood the question, then it becomes easy for you to interpret it and put it in the form of state diagram. Okay, so the first step is actually getting into your uh, question. Okay, so this is going to be your first step, understanding what your question is. And then the second step is going to be developing a state table, a state diagram. And if this is right, okay, if this is right, almost 50% of your problem is solved. Okay, so you should get at least this state diagram correct. So there is a breakup of marks for all the answers that you give. Okay, so it's all stepwise marking. So which means, say for example, you have started answering this question, and you have only given the explanation as to what is to be done, and you have given the state diagram alone, then probably instead of 5 marks, you should be getting at least about 2 marks. Okay. Then if you go ahead with the table, okay, if you go ahead with the table, then probably another mark will be added. If you go ahead with the excitation table and with the circuit excitation table, then another mark will be given. If finally you implement with the equations, then full marks will be given. So ultimately, what you should understand is everything is marks, with marks breakup. Okay, fine. So, so we will be seeing this problem where we are designing a synchronous 8-bit binary counter. Okay, so question is a very elaborately telling that it's a 8-bit binary counter. So when I say 8-bit, okay, so which means I need to take a binary combination from 000 to 111, and then it specifies to say that we are going to use JK flip-flops. Okay, so which means we need to understand how we get the characteristic table, how we get the excitation table of the JK flip-flop. Probably in my next lecture, okay, they will be looking, we'll be revisiting these flip-flops. Okay, and this needs to count the number of instances that the input coincident with the clock, okay, when the clock is high. So in simple terms, okay, whenever the clock is high, um, it should go to the next count. Okay, so that's the question. So let us take a 3-bit binary counter, okay, which has 2 raised to 3 or 8 combinations. Okay, because we have 2 raised to 3, which means it is 2 into 2 into 2, right? So this gives rise to 8 combinations. So when I have 8 combinations, how many states will I have, students? How many states
So
will
can
I
you
have?
repeat the question once again?
Yeah, if I have 8 combinations, okay, if I have 8 combinations, so how many states will I have? How many of these would I have?
Sure, three.
No, 8
8.
combinations means 8, right? 1, 2, 3, 4. So how many combinations I have here? How many
Eight.
do I have? 8 combinations, right? Okay. Fine. So since I have 8 combinations, it means I will have 8 states. Okay. So that is what I have written here, 8 states. Let x be the input, which is to be counted whenever its value is 1 at the instances of clock. So which means let x, okay, we will take x as the input, and this x will move on to the next value. Okay, it will migrate to the next value, which means x plus 1 happens. X plus 1 happens. When does it happen, x plus 1? Whenever I have my clock to be 1. If it's 0, if it's 0, then it will stay back in the same state. If it's 1, it moves to the next x plus 1. If it's 0, then it will be in the same state. Okay, so that is what we have written here. So since I have about 8 combinations, I will start with 000. Okay, so 0, 1, 2, 3, 4, 5, 6, okay, 7. So I have 0 to 7, which is 8 combinations, right? So let us say when it is 0, okay. Now what is this 0? What is the 0 referring to? What is the 0 referring to, students? I want you
That
to
is the
get back.
input.
Input. Input means what? Be specific.
Like if you're giving 0, it will stay at the same state.
So this 0 is referring to what? It's referring to the clock. Okay. Remember I had put a diagram, a pulse, right? So whenever it is 0, then it's going to be the same state. Whenever it is 1, then it will move on to the next state, right? So that is what is mentioned here. 0, same state. 1, 1, it moves to the next state. Okay, fine. So now you have to understand how this diagram has come. So I hope now you have understood as to how we have got these binary combinations. Yes or no? Any doubts here, students? Please be interactive, because this session, the sessions that we are going to have from now on, is going to be all your doubt clearing sessions. Okay, wherein you have to be interactive. You have to tell me if you have understood or not. So then it will be easy for us to discuss and continue. Right. So any doubts here as to how we got this? So I have a normal binary combination here going from 000 to 111. So when the clock is 0, I will tell my state to be the same. I will tell be the same state. Don't change your state. If the clock value goes high, okay, from low, if it goes high, okay, then I will say, when it's high, then I will say, okay, you're going high, so you move to the next state. So this 0 can also be represented as S0. This can be represented as S1. Okay, just for your understanding. Okay, now in order to rule out these, uh, these subscripts of S0, S1, and all those, what we'll do is we will just use directly the binary format. Okay, so that it doesn't cause confusion. If not, then you'll have to map S0 to 000, which means it's like a code. Then you have to map S1 to which format, to which combination? S1 to S1 will be what in binary?
001.
Correct. 001. Okay. So Similarly till S7. Okay, S7 will be what? 1, 1, 1. Okay, so this will in fact create more confusion in mapping, okay, the states and the binary format. So what we will do is we will not do this as of now. We will just keep this on hold. Okay, right. So it moves to the next state, which is 1, and then 0, it remains the same state. Okay, then 1, it's going to the next. So similarly, all this happens. Any doubts here, students, as to how we got this state diagram and how we understood the problem statement? Any doubts, please ask. Yes, no, any doubts?
No,
No,
sir.
sir.
Fine. So after we have this state diagram, so now we have to just put it in the form of tabulation. Okay, so how do I extract data now? I have to extract it in the form of uh, uh, my binary format. Okay, so as I mentioned previously, your X is going to be input. Okay, and your ABC, I will put them as your binary formats. Okay, so since I have from 0 to 111, okay, so my values are going to change. My values are going to change from 0, okay, till 111. Now, as you know, your X, okay, the input can either have 0 or it can either take a value 1. So I do not know either X is going to have 0 or 1 depending on the clock. Okay, so which means if your clock is low, okay, if it's a low clock, then I'm referring to X is equal to 0. If it's a high clock, then I'm referring to X is equal to 1. So depending on the clock, I have put this tabulation. Okay, fine. So now, as I always tell you, have a logical bifurcation here. Okay, try to have a logical bifurcation here, and yeah, so this will give you an idea as to how we are going about. Okay, so as you all know, your ABC is your inputs, and A plus, B plus, C plus, what are these? What are these? A plus, B plus, C plus?
So next state.
Correct. These are your next state inputs, right? So how will I predict? So which means I am predicting the future. Present state, I know what it is, and future, I want to know as to how it's going to respond. Okay, so how will I know that future state? Based on my state diagram. Okay, so here you can see that for every 0, okay, so I have 0 here and 0 here. So for that, I'm having 0 and 1 combination. For all the values, for all the binary values, I have to check for both 0 and 1. Okay, so from here to here, okay, it is 0, this is 0, then this is 1, 2, 3, so why do I have why do I have to write them two times, students? Why I'm writing them two times? Because I have to check for 0 and 1, right? For 0 and for 1, right? So now when it is 0, okay, when the input is 0 and your clock is also low, this input, what does it happen? Does it remain same or does it go to the next state? When your clock is 0, it remains in the same state. Okay, so which means I am going to have 0 only. In the next case, okay, for 0 input, when the value is 1, when the clock goes high, that means this state. When the clock goes high, then from 0, it migrates to 1. Any doubts here, students? Please ask if there is any doubts. All of you are following?
Yes, sir.
Okay. So similarly, you will be checking for 1. When clock is 0, it stays 1. 1. When clock is high, it goes to 2. 2. Clock is 0, remains 2. 2. Clock is 1, it goes to next state 3. Okay. Similarly, you can check from, you see the last case now. Okay. 111. When clock is high, it goes to the next state. Next state is 0. It doesn't go to 8. It doesn't go to 1,000. No. Why doesn't it go to 8? Can someone tell me? After 7, it should be 8, right? But why is it not going to this combination? Why is it not going to this combination after 7, after 111?
Sir, because it holds only 3 bits of data, like it cannot
Correct.
hold 4.
Correct. So since we are dealing with only 3 bits of data, so which means you can also refer to your state diagram. So after 111, it is actually going to the initial state, which is 0, 0, 0. Okay, so that's your state diagram. So which means after this 111, when the clock goes high, it will be going to its initial reset condition to 000, which means state 0. So I hope this table is understood by all of you. Yes or no? Can I move on, students?
Yes, sir.
Okay. So after this, now the question says that I have to use which flip-flop? I have to use JK flip-flop, right? So what I'll be doing, I will be using the JK flip-flop. So to make use of JK flip-flop, I need to know what is the excitation table of JK flip-flop. Now you should understand, for excitation table, we need to know the truth table. From the truth table, we get the characteristic table. From the characteristic table, we get the excitation table. Okay. So this is the last stage or the most refined table for a flip-flop, which is excitation table. So using this combination, okay, you can actually go ahead with this circuit excitation table. Okay. So how do we get it? Now, as usual, you have seen your cell number is there. Okay. Then you have A, B, C, X is there, A plus, B plus, C plus. So till here, we have seen in the previous table. The new columns that are getting added is these 3 columns and 6 entries. Okay. So that is nothing but your JA, KA, JB, KB, JC, KC. So these 6 entries are new. How do we get it? We get it from the help of these excitation tables. Okay. So now what you have to do is you need to have a bifurcation. Okay. You need to have a bifurcation here between each cell. Okay. So when I say bifurcation, it means you need to draw a logical line here and you need to understand as to how we are going about it. So to do that, okay, as I always mention, you need to make sure that you are comparing only A with A plus. Then you should be comparing your B with B plus. Then your C is compared with C plus. So only these 3 columns are to be compared with these 3 columns here. Okay. So how do we do it? Okay. So here you have to check for the value. So here I have 0. Let me get it right. Yeah. Here I have 0. And here also I have 0. So just check for 0, 0 value here, which is the first one, right? So for 0, 0, what do I have? 0x, which is don't care. So that is what I am entering here as 0, don't care. So here instead of don't care, I'm using a dash. Both are same. Okay, don't worry. In your examinations, you can either use a dash or you can use a X. Anything is fine. Okay, right. So similarly, now let us check for the next combination. Okay, so in the next combination, I have 0 and then I have 0. So which means it is going to be the same one. 0, don't care. So here also I get 0, don't care. So B plus JB, KB I should get. C plus JC, KC I should get. Right. So here also I have 0 and 0. So which means, will my combination change, students? Will my combination change? So I'll be getting 0, don't care. Yeah. So the only thing that changes here is it is called JCKC because I'm comparing C and C plus. So it is like here Q and Q plus, so J and K. So JK is general. So here I'm adding just the subscript A, B, C to both J and K. Okay. So students, any doubts as to how we got this first row, cell number 0? Was it clear? Anybody, any doubts, please feel free to ask. Yes, any doubts?
No, sir.
Okay. So similarly, you need to be very careful here, okay, when you are comparing. Say, for example, here you have 0, 0, 1, okay. So instead of 1, if you take a 0 by mistake, okay, then the combination is going to be wrong. Okay, so you should be taking 1, 0 as the combinations. But if you take 0, 0 as the combination, you'll be taking 0, don't care. So which means your equation here, instead of don't care 1, okay, instead of don't care 1, it will become 0, don't care. So ultimately your equation for JC and KC would be wrong. So if your equation is wrong, your implementation also will go wrong. Okay, so you need to be very careful when you are constructing this. circuit excitation table. So with this, we get our equations, which is nothing but JAKA, JVKB, and JCKC, right? So using these as the entries, okay, we will be individually using K maps for them. So separately, you should enter JA into a K map, okay, and separately JB into K map, JC, KA, KB, KC, okay. So all these should be entered into the K map. How will you enter? Will you enter row wise or will you enter column wise? How is the entry done? Row wise or column wise?
No. Sir, column wise.
Yeah, it should be column wise, right? So that is why I have written this cell number 0 to 15. So this will help you in the K map. So when I say 15, then you'll be using this value. You'll be entering this value in your K map. Okay, so for that, here also probably you can put a line. Okay, you can put a line here and use it accordingly. So all this 1, 2, 3, 4, 5, 6. So 6 K maps will be drawing. Okay. So once you have those 6 K maps, you will be getting all of these. All of this you will be getting. All of these equations. Right? So once you have those equations, I think it's very simple for you to get the circuit. Right? So here, as you can see, you are having BCX, CX, X, BCX, CX, X, CX, X. So I will have an AND gate, okay, which takes the multiplication of CX. So CX means these two are taken care. Then X means I will have KC and JC. So initially you can just draw 3 blocks, put JA, KA, JB, KB, JC, KC along with the clock. So this clock is given in common and JA, KA, JB, KB, JC, KC is again taken separate. Now, since we have both the values J and K same, okay, we short them, J and K, we short them. And here for KC, I have only X. So X I'm giving here. So this gets divided, okay, this gets divided and I will get the same X to my JC and the same X to KC. So in my next state, okay, in my next multiplication, I have CX. So if I work out for CX, it will work out for KB and JB. So that's why I have shorted both of them. So CX is a combination of or multiplication of C and X. So you have C and X. So this is where you get your output, right? So the same thing is given for your KB and your JB. Now, if I multiply again with B, okay, so CX will become BCX. Okay, so this is where I get my output, and this is given to KA and JA. So ultimately, I have got my K map, and then I have got my equations. From the equations, I am going and getting the final circuit. So students, any doubts with this concept? Yes, any doubts?
No, sir.
Okay, fine. So if you can understand this, okay, then it's going to be easy for you to try out with different flip-flops as well. Okay. Uh, in the previous class, I had given the SR, okay, to work out with SR. I think some of you have worked it out and few of you are yet to work out, right? So what you guys can do is take this question as a screenshot, okay, and start working with SR combination, okay. So take this as a screenshot, this question. Take this question as a screenshot. Design a synchronous 8-bit counter. Instead of JK, you use SR to count the number of instances that an input coincident with the clock is high. And try to work out for SR flip-flop. Okay, will you all start working on it? Okay.
With which flip flop, sir?
With SR, you can start.
Yes, sir.
SR. Okay. So for SR, what will you need? You will need your excitation table. Okay. So you can start working on it.